Hi, I'm Xingyuan Zhang. In this video, I will shortly introduce you our research work, Action Inference by Maximizing Evidence, Zero-Shot Imitation from Observations with World Models. This is a joint work with Philip, Patrick, and Max. Reinforcement learning has proven to be successful on many decision-making problems, but is notoriously sample inefficient when learning from scratch for a new task. On the other hand, we humans can learn new tasks fast and efficiently by observing others and imitating based on our prior knowledge. So in this work, we asked ourselves, could we replicate the imitation ability of humans with some machine learning models? To answer this question, we propose a simple yet efficient algorithm, AIME, to replicate the imitation process. AIME contains two separate phases. In the first phase, the agent is given an embodiment dataset where both the observations and actions are available. In this phase, the agent learns a variational world model to maximizing the elbow of the observation sequence. The elbow is an approximate lower bound of how likely the sequence is happening. In the second phase, the agent is given a demonstration dataset for a target task, where the only observations are available. AIME reviews the world model parameters learned in the first phase and formalizes the action sequence as another latent variables by introducing the policy. The optimization is done on the same elbow, with the only difference in the source of action sequence. So in the first phase, the action sequence is coming from the dataset, while in the second phase, it's come from the policy. In this sense, AIME solved the imitation learning problem by trying to find the best policy that makes the demonstration most likely to happen. To validate the proposed method, we conduct experiments on the Walker embodiment from DeepMind control suite with 3 tasks and a variety of settings. For the embodiment dataset, we take replay buffers, exploratory dataset, and we also mix all of them to have a more realistic setting. The demonstration datasets are collected by trained dreamer agents. We also designed 3 observation tabs from easy to hard. They are MDP, in which both position and velocity is provided in low-dimensional signals. LPOM MDP, in which only position is given in low-dimensional form. The hardest is visual, in which only position is provided in high-dimensional image form. Here we can see the results. In general, AIME largely outperformed the BCO baseline, even if we compare AIME on the hardest visual settings to BCO with the easiest MDP settings. And dataset does matters. It's not surprised that the closer the task, the better the transfer performance. However, AIME provides better generalization abilities when transferred between different tasks, especially when transferred from a P2E and exploratory dataset. Observation tabs matters, but not much. AIME is more robust to the observation tabs than the baseline. Difference could come from less well-trained models or high-dimensional observations. We also conduct evaluations on the number of demonstrations needed for AIME. We can see from the figure that AIME possesses 2 desired properties. The first is sample efficiency, that it requires 10 times less demonstrations to get the same performance as baseline. And the second is scalability, in which the performance keeps increasing as more demonstrations are given. Here we also provide some representative training curves to demonstrate the training dynamic of AIME. Here are 3 good cases where we transfer from the mixed dataset to the run task. We can see in good cases, the training process is very stable and fast. Elbow could overshoot to a higher value than the value with true actions due to some overfittings, but it doesn't have a big impact on the reward. On the other hand, here are also some bad cases where the visual models is transferred from random dataset to all 3 tasks. We could see that the training process is not that stable and mostly not converging. When it do converge on the run task, it largely overestimates the elbow. These failure cases are largely related to not well-trained models. If you want to know more details about the work, please check out our papers. Thanks for your attention.